5-10 minutes you'll do a group exercise. It's going to be fun, because after the example of matrix multiplication, we'll be jumping into the shortest path scenarios, which is really fun part of the course too, right? So just to refresh your memory, we talked about how to compute the matrix multiplication, right? When we had 3 matrices A, B and C, or in this case 2 matrices, and I gave you the formulation there, how each element is computed, and ultimately we said that we ignore the additions, and then we get the computation cost as P times Q times R, right? Because those are the total number of multiplications. And then we looked at an example here where we said if you have 3 matrices like this, right, which way of multiplying is better? It's A1, A2 followed by A3, or is it the other way around? We computed the multiplications and we decided that the A1, first multiply A2, A3, then multiply with A1 is the right approach to take. Okay, that was the example that we covered last class. Then this is where I glossed over the slide saying that we'll continue this one, because I glossed over it because we ran out of time. So we'll continue from here, and then we'll move on to the shortest path. Okay. Let me keep my chat window open. Yeah, perfect. So here is the notation, right? So let's follow it carefully. Okay, when I say Mij, that is multiplying Ij, cost of multiplying Ai to Aj. Okay, and then we are saying the cost is measured in terms of the multiplications, the scalar multiplications. If I equal to j, meaning Ii, then there is no multiplication, it's 0 by default. What we are looking for is to multiply 1 to n, different matrices. Okay, 1 n is greater than 1. Okay. Now, when you are multiplying, you can model that matrix multiplication as a binary tree. Okay, and each leaf is a matrix. And then, of course, as you build a tree, the intermediate nodes are nothing but the products. And the way to formulate that is, we say T is the tree. That is how we use it. Symbol T represents the tree. And remember, it's all dynamic programming. If you go back and review the rules, we said it's always about having the sub-programs. You're dividing a bigger program into sub-programs, and the sub-programs are yielding, there is some division of these things which yields optimal solutions, right? That was one of the optimality rule that we discussed. We also discussed when we have an optimality rule, that rule is not a bidirectional rule, right? You can have an optimal solution, we can have 2 optimal sub-problems, okay, but not necessarily the optimal bigger problem. The example that I gave you is that of the coins. Remember when we have the coins where we said we want to come up with an algorithm to come up with 13 cents, right? We said if we break into 7 and 6 cent sub-problems, we get an optimized solution for 7 cents and we get an optimized solution for 6 cents. But when we add up those 2 optimum solutions, the solution that we get for solving 13 cents is not optimal, right? So that relationship does not necessarily hold good. Then we said that if I can find a division of 11 and 2 as opposed to 7 and 6, the 11 and 2 yields an optimal solution going from bottom up as well. Okay, so how do we find those optimal sub branches is always a tricky thing in dynamic programming. Okay, that's where we left off. Okay, going back to this one here, when you have a tree here, you are going to represent the tree with a left subtree and a right subtree. So left and right, understood, pretty straightforward, right? So and the left subtree corresponds to multiplying, so that is one matrix. Remember, we are able to show this as leaves, right? Leaves and intermediate nodes. These are all matrices. We multiply matrix AI to AK. Okay. And then right one is obviously whatever is after AK, A plus 1 to AJ, because our indices are going from I to J. Okay. So this is one left subtree, B, and this is the other subtree. And the value of I is K is between I and J. So what is the cost here? The cost of the tree then would be cost of the right subtree, okay, cost of the left subtree, and then multiplying both B and C after that is computed. So it will be the cost of B and C. Remember, B is the left subtree and C is the right subtree. Okay. So technically, actually here, maybe if I make this one cost of B and cost of C, I don't know if that would make it readable or not for you. But if that is more readable for you, you can leave it as B and C. The reason why, at least at this point here, we say L and B is to denote the fact that it is left subtree and right subtree. So, sorry, I should be off. Okay, so that is the notation. Now, the trick is, remember, in dynamic programming, we are always saying that if you go back, and I'm assuming you reviewed this, these sub-problems tend to have similar characteristics. Okay, it almost looks like a recursive programming. Okay, I thought somebody would ask me that question. If you look at it carefully, when you go deep, you might get a question. Hey, what is the difference between dynamic programming and recursion? Recursion also is very similar, right? If you look at, like, for example, like a factorial. If I say factorial n, how do you calculate that one? Factorial n, that's equal to factorial n minus 1 plus factorial n minus 2, right? Other than the other conditions, if the n is 0 and if n is equal to 1, forget those two things, other than those values. So you're basically using a recursive function with 1 less and 2 less, right? If you look at the multiplication or dynamic programming also, the sub-problems tend to the interface looks the same, the behavior looks the same. Then what is the difference between the two? So think about it. I will answer that question after we finish the lecture. Okay. So here is when we do the recurrence relation, how do we compute the cost is what we are looking at here. Okay. So now when you compute the cost, if this particular line might kind of throw you off a little bit. This is nothing but you're computing cost of L, that is MIK, and then MK plus 1J is the cost of R, and then the cost of BC is two matrices, right? It's basically multiplying two matrices. When you multiply the two matrices, remember what did we say? We had that equation of P times Q times R, right? Where P, Q and R are the dimensions. P, Q are the dimensions of the first matrix, and Q and R are the dimensions of the other matrix. So this Pi, Pk plus 1, Pj plus 1 is nothing but these dimensions of the resulting matrix. Okay. So far so good. Now what is the challenge in dynamic programming? We do not know where to split that. What is that value of k is? Okay. Now how do we have to figure that out? We have to get the minimum of the cost for all values of k. So that's why you see this equation here, minimum of all the values of k between I and j minus 1. Okay. Some mathematics. I mean, I don't expect to ask you to write a formula like that in a final exam. At least not here. I don't know how they do it in India, but definitely not here. But the basic idea, as long as you understand it, hey, when I'm multiplying matrices, any two matrices, the cost is through the scalar multiplications, and then it is based on those dimensions P, Q, and R. So that's all this equation is saying here. And we don't stop it there, because in dynamic programming we compute it for all values. And that kind of has something to do with what I was telling you between recursion and dynamic programming. So if you have an answer, hold on to it. Full screen. Somebody is saying put it in full screen mode. Okay. I'll be happy to do that. Sometimes for me, when I put it in full screen mode, what happens is when I want to write, I cannot write on a full screen mode. That is the reason why I try to keep it in the other mode. Hold on a second. Something happened here. Okay, 1 second, please. If I put this in full screen mode, this one was not coming, right? Let me increase the size. Can you all see it better now? My cursor is jumping. Okay. Okay. If you still have difficulty, I'll try to put it in. I'll blow more than that. But this should do it for you. Okay. So here is an example of a matrix multiplication. So what is the goal here? The goal is to figure out what is the optimal way of multiplying. In other words, we transform the problem. It is basically breaking down that k, right? Which one way, what is the exact division? Similar to the exact division in the coin, here we are saying what is the way we divide this multiplication problem between these four matrices. Which one, if we do it first, followed by second, third, would result in optimal solution. Now how does the author do it? So here we have n equal to 4, meaning there are four matrices, A1, A2, A3 and A4. Okay. And if you go back and look at the formula, you will see the dimensions here. So you start with P1 equal to 3, P2 equal to 5, that is the next one. P3 equal to 7, that corresponds to this A3, P4 equal to 3, that corresponds to this, and there is a k plus 1 also in the dimension. Remember, when you finally finish it, you get this value. Remember, when you have PQR, you get P times R. So that last one, P5, corresponds to this 4 here at this point. Okay. Now once you formulate that, what you do is you are going to build a complete table. This is where we are getting into how dynamic programming differs from recursive programming. So what are you doing here? You are computing MIJs for everything. Okay, for each MIJ you record the k that gives MIJ its minimum value. So how do you read this table here? First of all, if you look at the first row here, M11, M22, that's the same row, but by default it is 0. Okay. Now when you look at M12, what we are saying here is, if you multiply matrix 1 and matrix 2, what is the value? You're with me? Okay. You just have to, it will take a little bit of time for you to, you have to think through it. Maybe you have to have a pencil and paper handy to get a full feel for it. Okay, so this M12 means multiplying matrix 1 with matrix 2. So if you go back here, matrix 1 is A1, that is 3 times 5, and matrix 2 is 5 times 7. So our rule is P, Q and R, right? What is the P here? P is 3. So 3 times Q is 5 times X is, I'm using X as times, okay, 7. So that is 15 times 7, that is 105, correct? So that is how you get that 105 there. Okay. Did I do any? Okay, there you go. I suddenly changed this index here. That's why I was worried. Okay, so now when you are doing it, you have all these matrices. What dynamic programming approach says is, hey, compute all the different permutations and combinations here. Okay, so if I do M12, I get this. It's you know the matrix notation, right? So you can easily if you look at the column wise here, you're seeing M11, M12, M13, M14. Then for 2, you're doing the same thing, M22, M23, M24. Okay, and then for M3 and M4. So you get a matrix of this shape. Now it's very easy for you to say that, hey, if you know the values. So if you look at if I were to do A1 and A2 followed by A3 and followed by A4, it's easy to compute the total. And when you compute the totals, you will see, because you'll get the minimum like this. Now this minimum is computed by this formula here. Pretty involved process, right? Actually, you're saying, is it too complicated, right? Can we do it in simpler ways? See, that is the reason why I said when you get into dynamic programming, it is how you do this. Yes, it's easy to say, hey, find the division into sub-problems in such a way it yields optimal solution. Now to find that one, it is a lot of effort involved. Okay, if you are doing it manually, actually it's going to take you more time, right? But since we are going to do it programmatically through computers, it doesn't matter. Even though it looks complex and counterintuitive, this actually leads you to a fully optimized solution. Okay? But the programming itself may look a little bit counterintuitive. Okay? It is. I give you an example when we teach programming like C or C, especially C, right? I'm not sure if you guys programmed in C, or if you programmed in C++, you will know C anyway, right? We have the concept of pointers in C programming, right? There are people who can write a 10-page code into one single statement using pointers. Okay? They start with a pointer to a pointer, then pointer to a pointer to a pointer. Somebody mute yourself, please. Somebody. Jntuk, I'm getting static. Please mute yourself. Pragati, I'm muting you. Okay, that was Pragati. Okay. Okay, great. So what it is right? So even if you, I doubt it if you understand what I just said 100%. Okay. If I'm in your shoes, I would take what is here and then I'll practice. These are the type of things where unless you practice, you would not fully understand the concepts, right? As long as you understand the general outline, how it is done, then you are in good shape. So and this example basically showing you how you compute these things, and then whenever you have to figure out what is the best way, you refer to this table. Okay, this table is called in general terms, it's called a lookup table. If you have done compilers, you would know what lookup tables are. Okay, there's some technical term that we use called meonization, not memorization, meonization. It's another big convoluted term to basically say we create some lookup table like this, so that way next time when you have to compute these types of tables, matrices, you don't have to redo the work all over again. It is in the table, you look it up. Okay, that is the key part of dynamic programming. Okay. Now this is a good point for me to go back and tell you that the recursion versus dynamic programming, right? So if you have like a if I have to create a slide here, we talked about Fibonacci, right? Not Fibonacci. What was the thing I talked about? N factorial, right? So when you do n factorial, say what? N equal to 0. What is the pseudo code here? N equal to 0, then 1, right? And n equal to 1, then 1, right? If not, what do you say? N factorial equal to n minus 1 n minus 1 parenthesis petty factorial పెడతాం కదా ఇక్కడ. Somebody is not audible. Can you hear me? Okay, perfect. Somebody said, okay, Jntuk underscore 49, they are not able to, Jntuk dot 49, they are not able to hear me. Chakravarti garu, please help them out. Jntuk dot 49, others are able to hear me fine. Okay, so this is the n factorial. Am I getting it right? N minus 1 factorial plus n minus 2 factorial. Something like this together. Faculty members, please help me out. I'm just doing it on the fly there. It's kind of like this, right? Now, when you go back here, now how do you calculate n minus 1 factorial? If I have to do, I have to put parentheses. So when you go to the n minus 1 in that recursion, so what happens when you do n minus 1 factorial equal to n minus 2 factorial plus n minus 3 factorial, right? Oh, I typed it wrong. N minus 3 factorial. Okay. So what is happening here is, if you look at these two steps here, right? The same factorial is being computed at every single step, right? There's a repetition. So in recursion, what happens is, if you, I don't know if when you learned recursion, your teacher would have told you, every single time you're computing n minus 2. Imagine if this n is a large number, these intermediate factorials are computed every single time, in every iteration of the program. You understand? Okay. If you take the same thing, I mean, if you look at the matrix thing that I showed you, what happens in dynamic programming when you do this, it is going to compute the factorials. Yes, that's true. That's what you do. Correct. SVCW, you're right. Okay. So when you do the dynamic programming, what happens is all these factorials are already computed. Remember, I showed you an example in the last class, right, where we said we go from 1, 2, 3, 4, 5, all the way up to n we compute, right? So it computes it all and puts it in a table. So next time, when you're trying to combine these sub problems into, it's a bottom-up approach, right? When you take these sub problems and try to come up with the solution, it doesn't need to recompute. It already just simply looks up the solution in the table. It's already there. So it's an access. We said it's stored in an array, right? A table is nothing but an array, a two-dimensional thing, right? It looks up. Lookup access is only order of 1, right? Instead of computing, doing all the multiplications. Initial workload is more, but once you compute those things and put it in a table, then the algorithm solves the problems very efficiently. Okay. Now it is all theory for you, but there are some examples here for you to convince yourself. Okay. And I'll give you more practice problems too. And after you learn these things, we'll do some computational analysis. How much do we save? For example, when we get into the shortest path problems, at some point I'm going to show you how different algorithms related to shortest path gives different. Okay. Okay, now let's see. Jntuk.49. I hope you solved the audio problem. By the way, SVCW, whatever you put here, I'm in terms of pseudocode, I think this is kind of pseudocode, right? And so on, right? And then you go back. Okay. Okay. Now let's get into, so we are still in dynamic programming. These are all the examples of dynamic programming. We looked at matrices, and we saw how dynamic programming helps in understanding the order in which matrices have to be computed. Now, in your numerical analysis class or linear algebra class, you would have learned the importance of matrices, right? I'm not giving you examples where we use matrices. Matrices are there everywhere. Okay. In a sense, the example that I asked you to work on is a matrix. If you have worked on it, you will realize it's some kind of a matrix there that I gave you last week as a homework assignment, optional homework assignment. Okay. Now we get into a second example, which is another classic example, and there are different ways of solving it. One is the traditional way. If you look at like a Dijkstra's example of shortest path and all that, I would call it like a traditional way. Dynamic programming helps us in solving these problems much more efficiently. So the focus of the next section is on this shortest path, and we call it all pairs shortest path. The reason why we call it is these algorithms that are there to figure out all pairs shortest path, what they typically do is they calculate the shortest path between every node pair. Node represents different things, right? Every node pair in a graph. Remember, when we talk about shortest path and all that, we talk about graphs, right? You model the problem as a graph. Like if it's a traveling salesman problem, we'll talk about that too. That's a graph. Routing of packets in an internet, right? When I send you an email, how does it get routed from here all the way to India to some Tom, Dick and Harry? That is the shortest path problem too. So we use this predominantly in very practical applications. Another application I can think of is I'm assuming you all travel quite a bit in India, right? Tourism is very big in India now, right? Everybody wants to go on vacation. Now, when you are doing those things, you would have encountered maps, right? Online maps or real physical maps. Or if you go to, like, for example, the railway station, online railway station reservation, you'll actually see the distance matrices there, which shows actually from station A what is the shortest distance to go to some station B, like different city. When I say station, I mean different city. So it shows like a diagonal matrix, which basically says, hey, here is the distances from this A to B, C, D, E, and so on. And then you go to the next row, it shows B, and from there E, D, E, F, and so on. So the applications of this are all over the place. Okay. Now, enough of lecture, right? Since it was a little bit theoretical and all that, I assume that I would have probably put some of you into sleep. Since I cannot see the videos, you can, even if you're conveniently dozing off, I would not be able to see, right? So I kind of guessed, so I wanted to wake you all up. So before I jump into the lecture, I wanted to give you a first group exercise. Okay? So please turn on your videos. Faculty members, please turn on the videos so that I get my wonderful group of students while they're working. Same modus operandi, groups of 2 or 3. What I want you to do is the following in the next, let's say, this might take about anywhere from 8 minutes to 15 minutes. Some groups can finish it in 8 minutes, some groups can finish it in 15 minutes. Okay? Let's give it 10 minutes. Somewhere in between we'll do, right? For the next 10 minutes, what I want you to do is answer these 2 questions. This is a graph. First, you have to tell me what type of a graph this is. Let's take the easy one first. Anyone can answer it in the. That's a no-brainer, right? What type of a graph is this? Based on our graph theoretic concept, what do we call this? You can put it in chat for now. Directed graph. There you go. SVCW, good job, thank you. It's a directed graph, right? Now, I did not tell you how to draw digraph, yeah? Short form for that. Excellent. If I can see the Jntuk Kakinada picture, I have asked people to raise their hands today. Chakravarti garu, you can make, there you go, right? Weighted directed graph. You are absolutely right. You are absolutely right. They are all the right terms. Okay. Now, what I want you to do is, right, I just said draw a matrix for a graph. I did not specify what type of matrix. Nothing. I didn't say anything. Okay. All I said was draw a matrix for this graph. How would you represent that graph in a matrix? Is what the exercise is. Understood? Okay. Ready, set, go. 10 minutes starts now. Sure that all of them are working. No, I could see them from my office. From here. I'll turn around. Yeah. Yeah, I can see Jntuk Kakinada video. Okay, I can see them working. I can focus them. I can see them better. How do you represent that matrix in a graph? Rather, that graph in a matrix. The other way around. Don't put it on the screen yet. JNTUV. I want them to think how they do it. There are different ways of showing it in a matrix. Jntuk Kakinada, don't put it on the screen. Right? The question that I asked was, is this an optimal path? That was the question that I asked. I wanted somebody to put this in the chat. That's when I lost my WebEx connectivity. Right? Remember, we're solving this traveling, sailing salesman's problem here, right? That is not an optimal path. You are absolutely right. Okay. Okay. Now, how do we fix that? How do we fix that? How do we fix the problem? That is the question, right? Right? Somebody said Jntuk Kakinada privately, they gave other paths, right? How do we fix this issue is the question, right? So that's why we are talking about all pair shortest paths and all that. So we will see how we fix that, okay? Students, I want you to be all pair shortest paths and all that. For the next 15 minutes, focus on each. Look at that. The other way of looking at it, to look at the optimal path, is doing an exhaustive search, right? So some of you put the answer in there, that's perfect. Now, how do we do exhaustive search? How many paths are there here? There are total 18 paths for exhaustive search. Okay, right? How did we get to 18? If you look at going from left to right, there are three choices, right? From going from A to 3 of them. The stage 1. Stage 2 is another 3 choices again. Stage 3 is 2 choices, right? H and I. So BCD is 1 choice, that is 3. EFG is another one, that is 3. How you got those 3, you can see that I'm explaining, right? H and I is 2 choices and destination 1 choice. Okay. So, exhaustive ways of doing it. Small problem, not a big deal. 18, right? But too many nodes cannot do it. It becomes an exponential problem. Okay. Now let us follow this algorithm carefully. What we are doing, we are going to construct the shortest path stage by stage. Okay, that is what the next set of slides are. How do we construct that? Let's look at it here. This is where you are getting into the meat of this algorithm, right? So stage 1. So you are going to go from A to or 4 or 3. Okay, so first stage is B. So you go there and then you are saying that, okay, I know the values from A to go to B, 2, 4 and 3. That is 2, 4, 3, and then I'm going to pick the 2 row. So you go 0, 0 to 2 row. So if you go over here, look at this slide here. 2, 4 and 3. That's what you got there, right? So stage A to B is 2, stage A to C is 4, and stage A to D is 3. Okay? We are computing all pairs. What are we doing here? We are doing all pairs shortest path, right? You are taking all the pairs of A. Pair is nothing but the adjacent in this case. In this particular case, it doesn't have to be like that. So AB is 2, 4 and 3. Okay, you got the first stage. Second stage is you go to E, right? The second stage is E, F and G there, right? So what do? We say AB to E you can go, AC to E you can go, AD to E you can go. Okay. Did I miss something here? Let me see. Okay. So when you look at the values here, you have 2 and 3 give you the same thing. Okay. You just pick one of them, right? So you say A, C and D. That's what the author picked here. Okay. Now, once you finish that one, then you're still in that second stage. Now you're going to compute for E, right? Remember? So we have ABE 279, 4 plus 3, 7. You pick ACE 7. So far so good. Once you pick, he is marking that with this was C node, remember, right? B, C and D. Okay, so you pick that one. Okay, then what do? Now you do the same thing for F. Every node you're doing it, if you notice that there. Every single node, right? For all the branches, for every single node you're doing that. So if you do that, you see that you get to do, sorry, I jumped there, sorry. I finished this. You're going to get ACF equal to 4. Okay? 4. You pick that one. Okay, then you do the same thing for the next node, which is G. So ABG, ACG, ADG. Both 8 and 8 are same. They just picked ABG. Okay. Again, let me go here. So you said you are going to pick that ABG route. So you can see that green arrow, how he made a solid line. Because there are multiple choices. If the values are same, which one you pick, right? So you pick that one. Okay, students, I'm assuming that you can put them in the chat and one of us will answer. Okay. Now we come to the third stage. Pretty exhaustive, huh? So we finished all the nodes in the second stage. We finished all the nodes in the first stage. We computed from A, B, all the permutations and combinations going from ABE, ABF, all these things. And then we highlighted the which arrow, which path we are going to take. Now you do the same thing for AEH, right? We are in the second stage now, right? Second to third, we are going there. So you do AEH, and then AFH, and then AGH. Okay, so he chose AEH equal to 8. We go there here. Okay, and you compute it for, and then you can see that they selected the path called AEH, and that with the solid green arrow they highlighted that. That is the path, right? Okay. Now after we do that, then we do I. We did for H, we need to do it for I. When you do the same thing from EFG to I, you compute, you see that you get 7 here. AFI, so you choose AFI. So when you do AFI, you highlight that in green. Okay. And then the last but not least, from those paths, you compute node J. So you have AH, J, and AI, J. When I say AH, right, I put dot dot because that entire path is there, right, in between nodes also. Okay, so then you get to 11. So it's AHJ. Right. Turns out you can go AIJ also, you get 11. Okay, let me pause here for a second. So that is the path. You get that. Okay, let me ask here. Questions, comments on that? Faculty members, add your wisdom to that, please do so. So what did we do in the process here? It's a pretty laborious one, right? You are basically calculating the distances between almost all pairs. That is what you're doing here in essence. And then after you do that, by putting it in memory, or the lookup table as we call it, or memorization as we say another term, I'll just call it lookup table for convenience, okay? When imagine if this was a solution in network routing, right? If you look at, I work at Cisco, we do a lot of routers and switches and things like that. This type of algorithms are used to figure out, it's not like they are computing those things dynamically. It has already been computed and it is stored in a table. I remember we used to call it internet messaging tables. If you take a networks class, you learn about these. These are called router tables. So we store this information. So when a packet comes to a given node and it needs to go to a certain destination, it already has this lookup table stored in that node. And then it routes the packet accordingly, which path to take. So very practical application of this. Wherever you go, it is there. Okay? Especially in networking. Okay, so that is one way of doing it. Is there another way of doing it? What did we do? We went forward, right? So if you look at the thing stage code, we started from the left side node, we went forward. Okay. Now there is a second way of doing it. The second way of doing it is backtracking. You can also backtrack the shortest path. Okay. Very useful concept. Okay. I don't think I want to go through how the backtracking is done, but you can convince yourself as to how to backtrack it. If you have to write an algorithm on a piece of paper, how would you backtrack? It's just the opposite of what we did, right? All we had to do is go back and see what are the arrows coming into me, right? So apply the same algorithm in reverse. That's all you're doing. Instead of going from A to J, you go from J to A. Okay? And then that also lends itself to the same shortest path. The answer should still be the same. Okay, let me stop here. Now I want to have some. Am I seeing the videos of the people? let's see, I can't see the participants. Let me see the participants. Okay. Jntuk Kakinada. Okay, show of hands now, right? I'm seeing the image of Jntuk Kakinada. Who has attempted to do this problem? The budget allocation problem. You all got busy watching some nice movie maybe, or you were too busy with other classes, right? I said busy with other classes, right? Give it a shot. I didn't say, give it a shot. I didn't you have to do it before you come to one. Even when I turn on my video, you may or may not. The question was, Jntuk Kakinada, can you solve the minimum coins problem using a bottom-up approach? See, that's what it is, right? If you look at the greedy algorithm, right? See, greedy algorithm is really a top-down approach, correct? So we showed actually the test cases where if you take the greedy approach, depending on the denomination that you choose, it may not work, right? There are, in the coin selection problem, depending on the denomination and all that, greedy approach says take the highest coin which does not violate the rule of what you're looking for, right? So you may not get an optimal solution from using the greedy approach. I think we showed that. If I'm not mistaken, we discussed that last class also. So what is the bottom line? Bottom line is, what this is telling you is, the moral of the story is, greedy approach is okay, but it's not necessarily the most optimal solution. To optimize, basically to optimize, what he says, you have to use dynamic programming. Okay, but now how often do we care about optimizing in real practical situations? You have all these IT guys writing this, right? People don't really pay too much attention to optimization. They are not hung up on that, because to optimize something requires more time, right? The DP algorithm, even the small things that we have seen, they are very complex. Number one, they are not easy to explain. Number two, they are not easy to understand. Now, when I go tell the manager, hey, this is how I'm going to solve the problem, the manager doesn't understand, right? If he doesn't understand, then I'm in big trouble. So you kind of compromise and sometimes go and use suboptimal solutions. I don't know if there's any study there. I'll be interested to pull up a study on optimization. I'll apply the 80-20 rule. 80% of the applications written are not optimized. I would even go as far as saying that 90% of the applications written in the industry, they are not optimized. Because optimization is a very difficult problem to solve. It takes time, money and resources. Okay? Now, none of you raised hands. So what we'll do is, because this has got to do with what we are learning. So I want to see, the goal is optimization, right? Dynamic programming. This is another dynamic programming problem. So what we are going to do, it is going to take at least 15 to 20 minutes to solve this one. Let's do it now. Again, I want to see the videos if possible. I want the students to come into groups. Remember, I make you work. It's all experiential learning. Unless you do it, you will not learn. And you do it in the class, so that way we all learn together. So what is the problem statement here? Problem statement is you have $5 million, you have 3 plants. Okay. Imagine it's like you have a rich dad, and dad has a lot of companies, and he says, I want you to allocate, you are now a Jntuk Kakinada graduate. When I say Kakinada, I mean Jntuk. Your dad thinks you learnt all these great techniques, and he says, I want you to invest this $5 million in my 3 companies. That is what it is. Okay? So they have all given you proposals. Okay, one company says, okay, give me 1 million and then my revenue growth will be this much. Give me 2 million, it will be this much, right? So that is what this table is. I kind of made you draw another type of table. These are all kind of related tables. Okay? Now the condition that we are imposing, each plant will only be permitted to enact one of its proposals, meaning once one proposal is accepted, all the other proposals from that company are no longer. And managing your dad's money is to maximize your revenues from the allocation of 5 million. Okay? Now whatever is not spent is lost. How do we solve this problem? We are talking about optimization, right? So how do we solve this problem? I want you to put your thinking hat. Again, do not put your answers there. Or you put it in privately, that's fine. Okay? So, by the way, I don't know the answer. Even I'll work with you. Right? We'll find out. Be rest assured, sometimes when I give problems, I should tell you this story. I was once teaching a database class, and I usually prepare my test the night before. If the day went well, the student get an easy test. If the day went bad, they had it right. I'm not in the right state of mind, I'll probably give a hard problem. So once I gave a problem that nobody could solve in the class. It turns out even I could not solve the problem. It is about functional dependencies and normalization. Even I could not solve it, but we learned a lot. Those kinds of things do happen in my class. But this problem I think has a solution. So ready, set, go, take time there, Andy, right now. 12:10 I think. 12:10. Let's spend time, the remaining time, trying to solve this problem because it has some nice meaning to what we are learning. Okay. For those of you who want to look ahead, the next topic that we'll get into is optimal binary search trees. Okay, that would be the topic for next class. Today we'll close the session by trying to solve this problem. Okay. The answer is not so fast to me. What I want is I want the students to work in groups. I don't know who is typing those answers, but I want the students to work in groups to come up with an algorithm. One right answer, or there are many right answers? You all understand the problem for today? In the remaining 18 minutes or so, we are going to solve this problem. Okay? Please turn on your video so that way I can see it, see your nice wonderful faces, and I can ask you questions in between how you're doing. Okay. This exercise, is it making you think? Why don't I do like this? Show of hands, SVCW. How many of you are enjoying doing this exercise? If you are enjoying doing this exercise, raise your hand. I'm looking at the video of SVECW. If you are enjoying doing this exercise, raise your hand. If you don't raise your hand, that means you don't like this exercise. you are saying, what is this professor? He is making us work hard. Right? Oh, you are raising all hands. Thank you. I should raise my hand too. I like giving those exercises. Exercises are fun. Okay, Jntuk Kakinada, you also can raise your hands since I can see your video. Only if you like doing this exercise. If you don't feel shy. If you don't like it, I will not feel offended, okay? Not everyone likes everything, right? 90% of the time I don't like what my professors teach. I shouldn't be saying that as a teacher. Truth be told, right? I can see JNTUV. Do you like the exercise? Raise your hands if you like it. I can see some hands being raised. Very nice. By the way, you don't have to be nice to today Mandava was very active, Vasavi was very active. I don't see their videos, that's why I'm not asking them to raise hands. It's been a while since I've seen Pragati's video. Very nice, I'm very happy for you guys. Let me open one other document and share it just to let you know, to give you a glimpse as to where we are. So let me open the file and then I'll share it with you in a second. Where is it? Next one. Yeah, there it is. Let me share this with you. Share application. So I'm sharing the syllabus here just to let you know students where we are. We are basically doing a lot of unit 4 right now. Right, we covered matrices, dynamic programming in general. I gave you some theory. We talked about multiplication, right? The matrix multiplication, how it is done. Knapsack we covered last week. What we are doing. Can one faculty member tell me what you mean by reliability design in this class? I was not quite sure what it is, what you people teach there, because I teach reliability in the context of software engineering. So I get deep into reliability, but I was just curious as to what we are supposed to teach here in this class on reliability design. Please feel free to send me an email as to what is usually covered in that, so that way I can address that. Somebody told me the last class is March. 2 units to go. We are in a comfortable position here to cover those 2. And in fact, I'm even thinking of dedicating the last week to basically review all the material. Okay, I'm seeing JNTV. How many of you made progress on doing the problem? Have you solved the problem already? Or you are in the middle of it, or you're... Don't feel shy. If you have solved it, why don't you ask your facilitator there to put your solution in the chat? JNTV, you raise your hands, right? Put your solution in chat, and whoever else solved it, put it in the chat for me. JNTV or any other college. JNTU Kakinada. You go through trial and error approach, okay? You can put it right. Tell them, I'm like almost like a 24 by 7 person. Sometimes I don't want the clock to be 24 by 7, you know. So what I do is I actually do what is known as do nothing time. So do nothing time is essentially I sit like a rock. That means I just sit. I don't read, I don't do laptoping, I don't do phone, Facebooking, nothing. I just sit, do nothing. Times. Okay, so Jntu we put 14282 and Jntu 141539. How do I read these your numbers? Can you explain, please? Oh wow, SVCW, that's fantastic. Sports meet, enjoy. Physical exercise is good for health, but learning exercise is good for mind. Absolutely. I agree with you. Solving puzzles is fantastic, right? P1, 1 to 5. So P1, you are saying that you are going to give them 1 and 5, you will choose that. And P2, you are going to give 2 and 8. And P3, you get 2 and 8. In P3, there is no 2 and 8, right? Yeah, I know plant 1. P1 is plant 1, and you are going to give them $5 million. There's only $5 million to give. So if you give all 5 million to P1, that means plant 2 and plant 3 get 0. Reading it. Not an easy problem, right? But then JNTU Kakinada put something there. Let me read it out. I think it was, they put it in private, I think, no? So you're saying JNTU Kakinada, explain to us what you mean by saving the sequence that satisfies the condition at last. What do you mean by at last? What do you mean by at last? I think that was a typo. So you by should I unmute you in case you want to talk? JNTU Kakinada? Oh no, we are over time, right? Okay, so what we'll do is, right, since we are over time, I mean, I'm happy to sit here as long as you want me to and listen to this. This is exciting stuff, right? Jntuk Kakinada said after evaluating all the possibilities, how many total possibilities you got? So you did an exhaustive search, right? Jntuk Kakinada says search, meaning they're computing basically, right? Okay. I think that's what I understand from them. SVCW 1 gets C1, okay, and 5 gets R1, 2 gets C2, okay. Okay, great. I think these are all, if you notice something, students, right? Different groups of people, they worked and they came up with different answers. If you notice that, right? That's an important lesson to learn, right? What we should do, in my opinion, is continue this conversation in the community. How about that? Okay? So, whatever you put here in the chat, Post your answers there with more detailed explanation, okay? Between now and Monday when we come back. Fair enough? So I'll say we will continue this discussion in the community. I will create a discussion topic. You post and explain your approach and answers. Make sense? Okay, any Chakravarti garu meeku any questions, any comments? Okay, Mandava, JNTUB, looks like you're all in good shape. You're still thinking about the problem perhaps. Okay, thanks everyone. Have a wonderful rest of the day, and I'm going that is one way of solving the problem. It is a backtrack technique. But you can explain that, how you applied that in the community, okay? Okay, so I am going to sign off.